Log on, tune in, find out. Another good idea from Cambridge.
20 years, I guess, on optical tomography. So we heard from Li Hong yesterday some of the advantages of optical contrast mechanisms, why they're of interest in medicine. And the photoacoustic effect is a very beautiful thing that gives you very high resolution. It has some disadvantages, but I'm mainly going to talk about just optical tomography in the classical sense, some modeling and inverse problems, and then some more recent advances using large data sets. And I will try to find time to mention a couple of things with photoacoustics as well. So the first point that people always bring up when you talk about imaging with light is they say that it can't be possible that you can see through the human body. And of course that's largely speaking true. Light is very strongly attenuated. It's both absorbed and scattered. And the principle and the effect of the scatter is that it increases the path length of an individual photon in tissue, and that means that it encounters more attenuating or more absorbing events, so that the overall attenuation becomes very extreme. But there are some interesting aspects, particularly when you look outside the visible spectrum, and what mainly preoccupies people in this discipline is this near-infrared region. And actually, historically, there's some evidence of this being used as far back as 1929, when a paper published by Cutler looked at the transmission of candlelight through breast tissue as a way of looking for lesions in the breast. But the main impact on the field in the modern era came with this paper in 1977 by Franz Jobsis at North Carolina, who looked at the exposed cortex of animals, particularly cats. So as Li Hong was saying yesterday, if you can do things invasively, you can image the surface of a tissue directly with a camera. You have a very high resolution, and this is what he was doing. But the main point that he was looking was spectrally and showing that you could see changes in the light at different parts of the spectrum being absorbed according to functional events, so that the metabolism in the brain is using up oxygen. It's taking blood from its red color, which is arterial blood, so purple color, which is venous blood, and you can just clearly map this in the exposed cortex of the brain. And this really gave rise to what became known as near-infrared spectroscopy. And this is a technique which is quite widely used. There's quite a lot of literature and quite a lot of active groups. It just involves a single source of light and a single detector, so it's just a one-channel system. And you look at the light that's traveled between the source and the detector, and you look at the change in concentration of various different chromophores, mainly hemoglobin, but also cytochrome. But of course, what's being done there is you're just globally measuring a change in whatever tissue, whatever path the light has gone through the tissue. So you can think of this as a partial volume effect and a lot of ambiguity in quantification. Nevertheless, people use this in a very simplistic way and relate just this single channel, this continuous measurement of multiple wavelengths of light to illustrate changes in oxygenated and deoxygenated hemoglobin and other tissues. And it's widely used to monitor hemodynamic processes, muscle, breast, and brain. And so what's called functional near-infrared spectroscopy is one of the armory of techniques in functional imaging. It's analogous to functional magnetic resonance imaging, in that you provide a stimulus and you measure a response. So that's a typical instrument. This is something experiment done in Birkbeck College near near UCL in London. So you can just mount this device on the head of a baby. It's completely safe. They're looking, in this case, at a screen with various images, and you're just monitoring here the pure change. You're looking at multiple wavelengths, and you're just simply doing a single channel inversion to get this change. And what you see here is this dotted square is where activation is, where the images come on, and you're seeing suddenly an increase in oxygenated hemoglobin and a decrease in deoxygenated hemoglobin. And then what? Sorry? This is time. This is the time of the experiment. So this is in seconds. So these early results led to development in the field, and where it's placed in the comparison modalities, it lies somewhere. It has very poor spatial resolution, so spatial resolution comes when we talk about imaging, which I'll talk about shortly. But in comparison with fMRI or PET, it doesn't compete. In comparison with EEG or MEG, you would have better spatial resolution, where it has slightly worse time resolution. The EEG is looking directly at the electrical response, whereas NIRS is looking indirectly at the reaction of the tissue to the electrical response. Well, if we try to quantitative determine the relationship between the intensity and the chromophore concentrations, then you start to face the problem of modeling. So we have this light scattering problem I already mentioned, and this is related to the path length. So individual photons go through extreme number of scatterings. So the individual path length has a probabilistic distribution. But if you can measure the time of flight of the photon, then you have a direct measure of that path length. So an early experiment in UCL, 1988, was the era when the development of fast lasers and fast detectors was becoming ushered in. So in these experiments, we take light of a duration of just a few picoseconds, input it into a sample, and then you can actually measure the distribution of the time of arrival of photons with certain technology. In those days, it was something called a streak camera. These days, there are some better quality measurement devices, but I won't talk about that. But the main point of this is that what you get is a distribution. So you get hardly any photons. The photons that are unscattered, what are called ballistic photons, arrive at the speed of light of a direct line of flight through the tissue, but there aren't really any of those. They start to build up this distribution. And what was shown here was that by taking different concentrations of scattering liquids in a cell with different absorptions, we can relate the change in the optical density. So the optical density is just log of input over output intensity, the same as you would measure with X-ray transmission, X-ray radiographs. Then it's almost linearly related to the mean time of flight of this histogram. So you just take the mean of this histogram, and we find that it's almost linearly related. This was just discovered empirically, but it turns out we can derive this also directly, theoretically, from a model based on diffusion equation. So if we treat this just as a random walk and take the statistics of that, it also brings out this relationship. So that meant that you could now quantify if there's some change now inside this volume due to activation, functional activation. It gives rise to a change in optical density, and now we can relate it directly to concentration through this time of flight, if we have such a thing available. But that involves this relatively expensive instrumentation of time of flight measurements. Okay, well, if we skip ahead now to the current era, this is what is now meant by optical tomography. So it's simply taking this principle and then multiplying up the number of channels. Instead of just using a single channel, you now have multiple channels, shown here with fibers with light delivered in the core of this fiber. So I won't go into all the details of that, but it's a fiber bundle. Light's delivered at the core and then measured at all these points around the head. This is just a rendering. This was achieved simply by putting that little cap device on top of a plastic doll and putting it in a CT scanner to get a 3D rendering. And then this is the box of tricks. This is the laser source. And it's all portable, wheels into a neonatal clinic. So this is inside a neonatal intensive care unit. This is an actual patient. And then how is the reconstruction done? Well, I'll be saying a bit more about it, but typically you produce a model-based method. We create a computational model using finite elements, and we just optimize the discrepancy between the measured and the model data. And we get these kind of 3D reconstructions. So this is showing a coronal slice through the head of this baby, and this is an ultrasound image taken as a validation. This is the ventricles in the brain. This patient had an intraventricular hemorrhage, so there's bleeding into this left side of the brain, and this shows up as this bright patch in this image. And that's just another view of the same thing, coronal and sagittal baby, so it's fully 3D. And then slightly later came another application which of course had a bit more influence because breast cancer is a very more prevalent medical condition. It's given a high priority. It's the cancer being the second highest cause of death after heart attack. Sorry, Bill. And this shows a patient lying, the same arrangement with the fibers rearranged into a cup and the patient lying, the breast inside this cup. We use a liquid coupling interface to simplify the model so that it's entirely a diffusive process rather than having to propagate from the surface of the breast to the tissue. Or that's something I will come to later. We can do that as well. And this shows the sort of image here. So this, what you see, of course, it's very low resolution. It's probably rather similar resolution you would get from EIT. Not very much worse than you would get from PET, actually. But here, this is a patient with a malignant tumor in the right breast, which is being imaged here. And the left breast, by comparison, is showing no such structure. And this is, again, a validation with a MRI with a contrast agent showing the breast, the tumor appearing. Okay, so that shows you some of the context for optical tomography. This is just purely that you input light and you measure with light. As opposed to photoacoustic, we input light and measure with sound. So how do we treat this? Well, of course, we treat it in a typical way. We regard the data as a forward mapping from a space containing the image through an operator to the space containing the data. But this must be treated non-linearly. If you're looking for the absorption and the scattering parameters, it's a non-linear mapping. If you double the attenuation, the absorption coefficient, you don't get half of the measurements. You get some more complex relationship. So there are, however, some linear versions that are also useful. So I'll come to that shortly. So one way we can analyze this, so we can regard the measurement as an operator M on the boundary measuring an internal field, which in this case is the photon density, which in optics is called the fluence. And this itself, of course, is just the result of a Green's operator, parameterized by the image we're looking for, acting on some source. And the source is under the control of the experimenter because we can place the fiber where we like. So when we regard this problem, we look identifying x from y. It's a nonlinear operation. It's a nonlinear inversion because g depends nonlinearly on x. When we're looking for just the source distribution, it's a linear inverse problem. And in some cases, we might want to do both of those things. We want to look for x and q. But what you can achieve depends strongly on what kinds of measurements you have available. So I'll start with this classical idea. Well, the basis we start with is the radiative transfer equation, which everyone here should know quite well. is the basis of the radon transform. So in a differential form, we could write this in this way as the one-dimensional derivative along a direction s hat of the field mu with an absorption coefficient u equals 0. So this would be the differential, this ordinary differential operator t along a ray direction. And so it just has an ordinary solution by integrating along this ray. So this would define the ray transform. We take the negative log of this and we find a linear relationship, the integral along this line between absorption and the measured projection. So this is the basis, of course, of the X-ray transform, the radon transform in CT, and it depends on the fact that there's no scattering here. So when we involve scattering, we have this extra term which involves this local scattering operator. And now the attenuation along the ray is affected by both absorption and scattering, because light is removed from the ray direction both by absorption and scattering into other directions. So this is how the RTE can be written in an operator form. And one solution method for this is to write a Neumann series for it, which is known the method of successive approximations in the book by Sobolev. It's very easy to understand. We simply take the source and we propagate it. So if we invert this transform, it just means the propagation along a ray. And if we propagate along this ray and scatter and locally and propagate again, and we repeat this, we get this series solution. We rearrange this a bit. We can take the first term here out. We take the source Q, we propagate it and scatter it, and we call this a new source along a ray. It's called the uncollided source term. Then we can just solve this problem for the uncollided flux, and then add back this uncollided flux plus this solution along the ray. Sorry, the collided flux and the uncollided flux to give the total solution. So if we do this kind of thing, so if we're now in the very weak scattering solution, you see, scattering case, we see that most of the ray is just propagated and attenuated along this direction. And as the scattering increases, it starts to broaden out. We're just sort of bringing up the scattering, and this ray starts to broaden out. And as scattering approaches the number of the mean free path in tissue, we're getting this much more randomly oriented or much more broadened out pulse. We still see here a little bit of the ballistic case, but as we increase the scattering, it becomes essentially completely broadened out. And this again, you saw Lehong mention the difference between the path length, the survival rate for the ballistic photons, which was about 1/10 of a millimeter, versus the path length of the diffuse photons, or the collided photons, which is more in a few millimeters. No, scattering is homogeneous here, but it was increasing in this series. Yeah. Well, the way that you proceed from the transport equation to the diffusion approximation can be done in a variety of ways, but a classical way is simply to expand this radiance in spherical harmonics and truncate it. So we effectively say that the radiance now is a term which is independent of direction plus one which is linearly changing as the direction of the current projected into the angular direction s hat, and there are no higher order terms. It's just a simplification, but then if we go through the algebra, you arrive at this second order diffusion equation. So the parameters now are d, the diffusion parameter, and mu a, which is the same attenuation, absorption coefficient, but g, where did I put g? Oh yes, sorry, 1 minus g. 1 minus g is, the g is the first moment of the scattering kernel of the phase function. So the effect of this is simply to give an effective reduced scattering coefficient. But in practical terms, we can just regard this parameter lumped together as one of two parameters we want to reconstruct. So there are plenty of other approximations which I won't have time to talk about. The telegraph equation is a second order in time, but they all have this dominant parabolic or elliptic behavior. And then in measurement technology, this was this original measurement technology we developed, which looks at the pulse of light and looks at this histogram of the time of flight of arrival. But equally well, you can do a measurement in effectively the Fourier transform of all this, where we put in a harmonically modulated light beam. So it's just equivalent to turning a light on and off, or with a sinusoidal variation. But it has to be at a frequency which is commensurate with the time length of this. This scale is of the order of a nanosecond, so we're talking about hundreds of gigahertz, hundreds of megahertz up to gigahertz frequencies here. And then what you measure, you eventually measure this in quadrature, and you get a complex valued response function. So what tend to be the way that we currently analyze things is we measure in this time of flight. This has certain advantages, which I won't talk about right now, but we analyze it in the Fourier domain. So we simply Fourier transform the received signal and analyze it in the Fourier domain. And as we showed in 1998 with Bill, of course this was something with hindsight is extremely obvious, that if you measure only the number of photons, so if we have frequency 0, we just have a constant light source, you get a Dirichlet to Neumann map of a real valued number, and we can from that reconstruct only one real valued coefficient internally. So it's impossible to disentangle the absorption scattering uniquely unless we have access to either this time or frequency measurement. If you don't have that, you can only recover effectively the product of absorption scattering, almost with some modification. All right, so then how might we tackle the inverse problem? Well, a classical way is to use a perturbation approach. So if we now think of the PDE governing the propagation as L, parameterized by x, and now we're starting at a state x0, which, let's say we have a reference measurement at x0 and then a small local perturbation. This defines a potential operator. And then if we go through steps of deriving a Lippmann-Schwinger equation and then expanding it in the series, we would get this general Born series, where we would say that the mapping in the presence of the perturbation is the unperturbed mapping plus this kind of expression. So this involves the field U acted on by the potential and then propagated with the Green's function. So this has this classic idea that we have an incoming field U, we have a perturbation, and then the propagation of the perturbation from here. And this is just given by the Green's operator acting on the product of this perturbation or the compounding of this perturbation operator on this initial field. And then we can also derive this, we can take this a step forward, because rather than thinking just of the measurement of the intensity, we might want to measure a transformation of the intensity. So typically we want the logarithm of the intensity. So we just take the logarithm, of this operator, and we can develop other series. So typically the write-off series is derived by taking the expansion of the logarithm of this operator. And then when we do it numerically, we simply project everything into a basis. So we define a basis to represent the fields. So if we're using majority of results we do with finite elements, we produce a discrete finite element representation of the field. Another representation for the image, which is typically we would use just a pixel basis here, and this would be the basis imposed by the finite element mesh. And then if we just go through the classical discretization and variational approach, we just arrive at a numerical method. So now the operator G is represented as the inverse of a sparse matrix. Q is a vector, and M is a measurement vector. And then we're in the realms of optimization, and we can simply so we're simply in the rate of saying now we differentiate this forward operator, or the PDE, discretized PDE, we split it into partial terms, ki, which is dk by dxi. And then we have this representation of the first term in the Born series, which is the forward solution. This is now the discretization of the potential at a pixel, and then the measurement. And then if you look at this form, you see that this mk inverse is just the adjoint field that we get by taking the measurement operator and propagating it backwards. So the forward field is propagated, so this should be u, sorry, is propagated from the source, the adjoint field from the detector, and then they're interacted here. So we just represent this as this derivative matrix operator on u with the adjoint operator. And this forms the discrete Fréchet derivative of the forward mapping, which is numerically sometimes called the Jacobian, or the sensitivity matrix, maybe what it's called in EIT. So that's the basis. The first ideas were like this. We just build this matrix explicitly, measure the difference between the field and the perturbation of the field, and invert this. And so, generally speaking, we're using a regularized output least squares method. There are some other possibilities, but this is all I'll talk about here. So you define this objective function, which is, of course, in the Bayesian sense, is the maximum a posteriori as the sum of a negative log likelihood term, which is the data mismatch, and a regularization term. And because this is nonlinear, we need to solve it with some nonlinear method, and it's just classical optimization. So a typical way to do that would be Gauss-Newton. You end up with something that looks like this, where we're iteratively updating the image. This is the residual, the difference between the data and the model at the current step. This is the covariance of the noise process, the measurement noise. This is the adjoint Fréchet derivative, the derivative of the regularization step. And this is this inversion, which is the adjoint Fréchet derivative, the noise covariance inverted, and the forward Fréchet derivative, and H is the Hessian of the regularization term. But when you start dealing with large-scale problems, as many people know, when we start to invert with a very large number of variables, this becomes somewhat infeasible because we have a very large matrix to invert. So we prefer to look for other methods. And one we found particularly appealing is the Krylov method, where we simply construct an initial Krylov basis vector, which is just the gradient of the optimization of the objective function. And then at each step, you form the next Krylov step by forward projecting, filtering. This is a smoothing operator in the data space, and then back projecting, and then filtering in the image space with the inverse of the Hessian, which again, the regularization term is typically a local PDE. So this is again a smoothing operation. So by constructing this series with relatively few terms, we can solve this, the linear part of the nonlinear inversion quite efficiently with just relatively small, typically 6 or 10 Krylov basis vectors. And furthermore, we can do this entirely in a matrix-free framework, because we never need to actually construct this explicitly as a matrix. We simply can form it by the action of the forward and adjoint fields on the left and right hand side. So we have a fully matrix-free inversion step that allows us to tackle quite high-dimensional inversion problems with relatively cheap memory requirements. So now let's just go through some of the problems that are addressed in optical tomography. So this is the typical performance of this, what I started with, this classical optical tomography, which means that you are just doing a parameter identification. If we're sticking to the diffusion equation, we're talking about those two parameters, the absorption and diffusivity. But because of the relationship between diffusivity and scattering coefficient, we can also formulate it equally well. It's just a change of variables to reconstruct this parameter mu s prime, which is what someone asked about, Adrian, which was the product of mu s and 1 minus g. So this is we can choose to reconstruct either of these, and we just form this linear operator as just an integral operator with this is the form it takes, the product of the forward and adjoint for the absorption and the scalar product of the gradients of those fields for this diffusion parameter. And then this is a typical result. This is a phantom, a numerical phantom with various objects with different sizes and different contrasts. So on the left, the first column is the absorption coefficient, target distribution, and this is its reconstruction, and this is the scatter distribution and its reconstruction. And this is done with a typical way where you use a high resolution mesh to generate the data, you use a lower resolution mesh for the reconstruction. We've add multiplicative noise proportional to the measured intensity. So you see that we can reasonably well discriminate between absorption and scattering, and also you see this low resolution aspect of the reconstruction. This is the method that's used for those initial images I showed you of the brain and the breast. Well, as I mentioned, we can also look at some linear problems. So if we now turn to the idea of looking for the source rather than the parameters, we can specify a couple of different identification problems. The first one, it's not historically the first one dealt with, but it's easiest to think of, is called bioluminescence. And this is simply, biologically, there are certain molecules which will just emit light spontaneously. They're just like, they're based, same mechanism we have in a firefly. It's called luciferase, and it just radiates light. You can attach it to certain molecules like drugs, put it into the tissue, and then you just basically imagine you were following a firefly in a fog. Then you measure all around, you get multiple images of that firefly, and you want to identify its position. So now we're measuring here. We don't have control over the source. We're trying to identify the source, and we only have one measurement on the boundary. So we have dimensionally a shortage of information, because in 3 dimensions you measure on a surface, so you have a 2-dimensional function. You're trying to reconstruct a 3-dimensional function. You can think of this as the optical analog of SPECT, single photon emission computed tomography, if you had no collimation. So in SPECT you're typically measuring also the direction, so you have measurements in position and direction and reconstructing the source position. But now if you threw away the directional information, you have a non-uniqueness. So it's more analogous to what happens at EEG, where you're measuring a potential on the surface of the scalp, and you want to reconstruct spontaneous electrical sources. In that case it may be dipoles as well, which doesn't have an analog in optical. But as well known, this is a highly non-unique problem. So what could we bring to assistance? Well, one proposal has been to produce, to use multiple wavelengths, so that you get the 2-dimensional map on the surface at multiple wavelengths. This was proposed by Alexandrigas in the early 2000s. So if we look at how that works, here you see, now I'm just showing a source here, 2 sources, and this is just the spontaneous field. So taking this as a source and just propagating the light, it's just diffusing away if we could measure internally. But of course what we measure is on the boundary. What we measure is on the boundary. So if we took the boundary measurement of this and tried to reconstruct internally, we wouldn't be able to do it. Now if we look at multiple sources, because multiple wavelengths, because the attenuation is different, we get slightly different measurements. So again, it's not completely clear with I don't know if it would help to turn the lights out, probably not, but you might be able to see that this is decaying more rapidly than this, because here the absorption is higher. So now if we take these multiple measurements, we have a set of operators at each wavelength, and we get access to a reconstruction. But the thing is that they're very highly correlated, because the measurement we get, as you can see, this internal fields only differ slightly. So because of this high correlation, this is still a strongly ill-posed problem. It's not actually non-unique anymore. So we can recover this low-resolution image. Now, the alternative to this is fluorescence optical tomography. And here, the idea is that you put into the tissue light. It's exactly the same mechanism, but now this potential is absorbing and then re-emitting the light at a longer wavelength. So if you put in blue light and re-emitted it at red, you could then put a filter here and measure only the emitted light, the fluorescently emitted light, and not see this background light. And then your contrast that you see in the measurement is much higher, because instead of, imagine looking at a sheet on the washing line and it's got a slight discoloration to it, you're seeing a very bright light and you're looking for a slight variation. Now you take away the background, you would see this much higher contrast. And again, this can be chemically constructed. Again, you heard something about this from Li Hong Wang, the basis of the Nobel Prize a few years ago in chemistry. But from our mathematical point of view, we have control of the excitation, so we have a richer set of data. And now we construct again an inverse problem, where now we have a set of operators A for each of the sources that each of the excitation sources that we put in. So now it looks a bit like this. So we take the same problem here. Now imagine that we're illuminating it. I think we start here. We're generating an internal field. Then we multiply the field with this and propagate it again. We get this distribution. Now as the source now rotates around, so here the source is coming in from this, no, probably from this direction. I think I went around this way. So now you see that that as we take the source around, we're seeing this structure here now has quite a lot of information in it, as opposed to the previous slide, where the structure looked only very slightly different, so they were very highly correlated. Now we have less correlation, we have more information from the fluorescence. So now we can get a higher resolution reconstruction. Some experimental aspect of that. This, what was just described, is a purely linear process, because we're assuming that the parameters are known, but of course in reality they aren't. We have the same parameter identification problem we started out with for the parameters at the excitation wavelength, and strictly speaking we should also have that at the fluorescence wavelength. But in this case we're just doing a simplification of this, assuming that we are measuring the excitation with the classical optical tomography plus the fluorescence, stimulating the field with the source coming from this excitation. So this is an experiment done with Vasilis Zia-Christos when he was still in Harvard before he moved to Munich, just showing illumination with fibers here in a square cell and then looking at it with a camera. So I'll come to the camera if I have time say some more details about that. But from this point of view, you would treat this camera, you could treat each pixel of the camera as like a fiber. But there are many, many more, of course. So we start to get a larger data set. But I'll come to that in a moment. But for now, we can just think of it the same way. We just have a set of sources. For each source, measure all these points. And we put in absorption and scattering rods. And we see that, let's see, this is an absorber. These are two fluorophores. And we try to reconstruct both the absorption and the fluorescence. So looking from the top, these are the absorbers. These are the fluorophores. This is the absorber. So this absorber here is subtracting some photons that are detected on this side. So if we ignored this effect here, we would see less signal from this fluorophore, and we would get a reduced amplitude in this reconstruction. But as you see here, the two amplitudes are almost equally well reconstructed, and the absorber is determined to be at this point. What you see here is just part of the bad ill-posedness of this. There's no TV regularization or so on. This is 6 or 7 years old slide, so that this is actually should be a vertical rod instead of this bell shape. Okay, then if we take this up into time domain or frequency domain, that's not. My phone is off, so I'm not sure what that is. If we take this up into time domain or frequency domain, everything is quite similar, but now this parameter becomes a complex number. And the process in what's called fluorescence lifetime optical tomography is that not only do you consider the number of photons that are being emitted by the fluorescence, but also that delay, because the emission is a Poisson process, so it has a half-life. and the half-life is affected by the molecular environment. It's very similar to the effect you see in MRI with what is called the spin lattice effect that gives rise to this difference between the T2 parameter in MRI. Sometimes people have used the term for this fluorescence lifetime optical tomography, they call it optical MRI, because you can play with the lifetimes and the concentrations and try to reconstruct them both, but it's compounded by this extreme nonlinearity and ill-posedness. But from our point of view, we see this as a complex number, and we can just separate it into the concentration of the fluorophore with the product of the Fourier transform of a Poisson decay, which is this Lorentzian term. So the key factor is just this lifetime. Whoops, I keep doing that. The key factor is just this lifetime tau. So this becomes this additional parameter to image here. So our task is now to reconstruct both the concentration and the lifetime of this parameter here. Here's a couple of seconds. So this shows one result we did with Imperial College. Again, this mesh, and here are different things that we're looking at with this is scatter reconstruction, absorption reconstruction, fluorescence concentration, and lifetime, all 4 parameters being in reconstructor. So let me skip on. This is just showing the effect that you have different lifetimes in, this is real data from a mouse, the different lifetimes, as I mentioned, due to the molecular environment. That's due to something called resonant energy transfer, which I won't dwell on. Let me skip this multispectral stuff and just mention about multimodality. So again, something that's being researched quite actively is the combination. So this is not hybrid imaging, which you're going to hear about in the next talk, or photoacoustic, which is where the physics is coupled. This is uncoupled physics, but simultaneously measured. You measure the X-ray image, and we measure the optical image at the same time. And then we can make use of reconstruction with anatomically constrained priors. So we can construct priors which are based similar to TV or paranormalic, which are based on the gradient of the image that we're trying to find, weighted by geometrical information. So it takes this form. If you know that first variation of these looks like an anisotropic diffusion process, the form of this function controls whether we're dealing with TV or paranormalic, but the form of the weighting is dependent on the X-ray image. So here now we see kinds of things we can do. This is a mesh now. We impose on this mesh the boundaries in the X-rays, and we get this kind of quite nice reconstruction restricting the fluorophore into the brain of the mouse. So now I have gone a bit too slowly, so I'll just go to the end. So the main interest in optical tomography is because of the spectral contrasts that relate functional activity of tissues. It's low resolution, similar to EIT, but relatively fast. Most of what I showed here was based on the diffusion equation, but the transport equation is an alternative, and there's a long debate which I won't be able to go into here about the relative merits of those. It's quite a difficult topic. We need to look, if we look at systems based on time flight or frequency, we have a richer set of problems that we can try to address. So I didn't manage to say something about data compression or photoacoustics, but I'm happy to talk with anyone later about that. And lastly, I'll just mention over the years many of the collaborators that I've been fortunate to work with, so I better stop. Thank you.
We'll take a couple of quick questions.
Going right back to the beginning, Simon, about the Neumann series expansions and things like that. Do you have any control on the convergence of those expansions? I mean, you've just taken off the first term, but do you have any results about the convergence of those sort of series?
Well, generally speaking, if you're looking in L2 norms, they're easily defined as being convergent because you have a physical interpretation that the propagation, each of the Green's function terms is attenuating, so the power of each of those terms is diminishing. In other norms, like L infinity or L1, it's slightly tricky, but there are results that show that that's convergent. Yes.
In that case, we'll move on and we'll take the speaker again.